Welcome to Cosmic Whispers, where cosmic mysteries come alive. Your journey beyond the stars begins now. The journey to power our civilization has been one of constant evolution. From wood to coal, from petroleum to nuclear, humanity has continuously sought new ways to fuel its ever-growing energy needs. Today, we face perhaps our greatest energy challenge yet: how to power a global population of 8 billion people while simultaneously addressing the climate crisis that threatens our very existence. Every second, our planet receives more energy from the sun than humans use in an entire year. The numbers are staggering: 173,000 terawatts of solar energy constantly bombard Earth's surface. In comparison, human civilization's total energy consumption hovers around 18 terawatts. Mathematically speaking, this means the sun provides over 9,000 times more energy than we currently need. Yet despite this abundance, solar power generates only about 3% of global electricity. The question isn't whether there's enough solar energy, there's more than we could ever use, but rather if we can harness it effectively, efficiently, and economically on a planetary scale. To understand this challenge, we must first comprehend the immense scale of global energy consumption. In 2024, the world consumed approximately 170,000 terawatt-hours of energy. This enormous figure includes everything from powering homes and businesses to fueling transportation systems and manufacturing processes. Every great journey starts with a few brave explorers. Right now, Cosmic Whispers is just beginning, and your support means everything. If you enjoy unraveling the mysteries of the universe, hit subscribe. It's free, and it helps us grow this community together. The theoretical potential of solar energy dwarfs our needs, but theory and practice often stand separated by chasms of engineering challenges. These challenges include intermittency issues: the sun doesn't always shine, storage limitations, transmission inefficiencies, and land use constraints. Consider this: if we were to power the entire planet with today's solar technology, we would need approximately 0.3% of Earth's land surface, an area roughly the size of Spain. While this may sound substantial, it represents less than 2% of the world's desert land, areas that receive optimal sunlight and are typically unsuitable for agriculture or human habitation. The physics behind solar energy conversion starts with photons from the sun striking semiconductor materials, typically silicon, which release electrons and generate an electric current. Modern commercial solar panels operate at approximately 20 to 22% efficiency, converting only about 1/5 of the sunlight that hits them into usable electricity. Laboratory prototypes have achieved efficiencies exceeding 47%, hinting at the untapped potential of future technologies. Meanwhile, the theoretical maximum efficiency for single-junction solar cells, the most common type, stands at approximately 33%, a limit known as the Shockley-Queisser limit. But the solar revolution isn't just about photovoltaic panels. Concentrated solar power technologies use mirrors or lenses to focus sunlight, heating fluids to drive turbines. Solar thermal systems capture the sun's heat directly for water heating and space conditioning. Emerging technologies like perovskite solar cells, organic photovoltaics, and solar fuels promise to revolutionize how we capture and store solar energy. As we stand on the precipice of this potential energy transformation, one question looms large: could we actually run the entire planet on solar power? The answer requires a comprehensive examination of technology, economics, geography, and human behavior, a journey we'll undertake together. The fundamental mechanics of solar energy capture have evolved dramatically since French physicist Alexandre-Edmond Becquerel first observed the photovoltaic effect in 1839. Modern solar energy systems fall into two primary categories: photovoltaic (PV) technology, which converts sunlight directly into electricity, and concentrated solar power (CSP), which harnesses the sun's heat. Photovoltaic cells, the building blocks of solar panels, operate on a quantum mechanical principle. When photons strike a semiconductor material, typically crystalline silicon, they transfer energy to electrons, freeing them from their atomic bonds. The cell's structure then forces these electrons to flow in one direction, creating an electric current. This direct conversion of light to electricity occurs without moving parts, combustion, or emissions. Today's commercial solar panels typically achieve efficiencies between 20 and 22%. While this may seem modest, it represents a remarkable improvement from the 6% efficiency of early solar cells from the 1950s. The theoretical maximum efficiency for single-junction silicon cells is about 33%, limited by the Shockley-Queisser barrier, a fundamental constraint based on the band gap of silicon and the spectrum of sunlight. However, emerging technologies are pushing these boundaries. Multi-junction cells, which layer different semiconductor materials to capture various portions of the solar spectrum, have achieved laboratory efficiencies exceeding 47%. Perovskite solar cells, thin film technology using synthetic minerals with excellent light-harvesting properties, have surged from efficiencies of 3.8% in 2009 to over 25% today, representing the fastest efficiency improvement in solar technology history. Concentrated solar power takes a different approach. These systems use mirrors or lenses to focus sunlight onto a receiver, heating a transfer fluid to temperatures reaching 700 degrees Celsius. This heat then drives conventional steam turbines to generate electricity. Unlike photovoltaics, CSP systems can incorporate thermal storage, allowing them to produce electricity when the sun isn't shining. The industrial-scale deployment of solar technology introduces additional challenges. Manufacturing capacity for solar panels has grown exponentially, with global production exceeding 200 gigawatts annually. China dominates production, manufacturing approximately 75% of the world's solar panels. This centralization raises geopolitical and supply chain concerns, particularly regarding critical minerals like silicon, silver, and rare earth elements. The carbon footprint of solar manufacturing is another consideration. Producing solar panels requires energy-intensive processes, particularly in purifying silicon to the 99.9999% purity needed for photovoltaic applications. However, life cycle analyses consistently show that solar panels pay back their carbon debt within 1 to 4 years, depending on their location and the energy source they replace. Scale presents both opportunities and obstacles. Utility scale. Solar installations benefit from economies of scale, with costs per watt significantly lower than residential installations. The world's largest solar farms now exceed 10 gigawatts in capacity, enough to power millions of homes. The Bhadla Solar Park in India and the Golmud Solar Park in China exemplify these massive installations, converting desert landscapes into renewable energy powerhouses. However, the intermittent nature of solar power remains its greatest technical challenge. Even in optimal locations, solar panels typically operate at full capacity only 20 to 25% of the time, compared to the 90% capacity factor of nuclear power plants. This capacity factor disparity means that a solar-powered grid requires substantial overbuilding and complementary technologies. The sun delivers abundant energy, but not continuously. This fundamental reality that solar power is inherently intermittent represents perhaps the greatest challenge to a solar-powered civilization. At night, during storms, and in winter months, solar generation drops dramatically or ceases entirely. In northern latitudes, the seasonal variation is particularly pronounced, with winter production falling to less than 20% of summer levels. This intermittency creates what engineers call the duck curve, a graph showing net electricity demand throughout the day that increasingly resembles a duck silhouette as solar penetration increases. During midday, solar floods the grid, sometimes producing more electricity than needed. Then, as the sun sets, demand typically peaks while solar production plummets, requiring other sources to rapidly ramp up. To run the entire planet on solar power, we need massive energy storage capabilities operating across multiple timescales, from hours to seasons. Battery technology represents the most developed short-term storage solution. Lithium-ion batteries, which power everything from smartphones to electric vehicles, have seen stunning cost declines, falling by approximately 90% since 2010. Grid-scale battery installations now exceed multiple gigawatt-hours in capacity, with projects like Australia's Hornsdale Power Reserve demonstrating their ability to stabilize grids and shift solar production to peak demand hours. However, lithium-ion batteries face limitations for long-duration storage. Their energy density, while improving, remains too low for seasonal storage at a reasonable cost. Their reliance on lithium, cobalt, and nickel, minerals with their own supply challenges and environmental impacts, also raises sustainability concerns at the massive scale required. Alternative storage technologies offer promising solutions for different time frames. Pumped hydro storage, where water is pumped uphill when electricity is abundant and released to generate power when needed, accounts for 95% of grid storage capacity today. With round-trip efficiencies of 70 to 80%, these systems can store energy for days or weeks, but require specific geographical features. Thermal energy storage, particularly coupled with concentrated solar power, stores energy as heat in molten salts or other materials. These systems can discharge for 10 to 15 hours, bridging the nighttime gap. Compressed air energy storage uses excess electricity to compress air in underground caverns, releasing it to drive turbines when needed. Emerging technologies like flow batteries, which store energy in liquid electrolytes, promise lower costs and longer durations than lithium-ion systems. For truly long-duration storage, spanning weeks or months, chemical energy carriers show the most promise. Hydrogen produced through electrolysis using solar electricity can be stored indefinitely and used in fuel cells or turbines when needed. Synthetic fuels created from solar-generated hydrogen and captured carbon dioxide offer another pathway, leveraging existing natural gas infrastructure and storage capabilities. The cost of storage remains a critical factor. Current lithium-ion battery costs range from $150 to $200 per kilowatt-hour, projected to fall below $100 by 2025. However, models suggest that powering the US with solar and wind would require approximately 3 weeks of storage capacity to maintain reliability through extended low production periods. Transmission infrastructure represents another approach to the intermittency challenge. High-voltage direct current HVDC lines can transport electricity over thousands of miles, with losses of only 2 to 3% per 1,000 kilometers. This enables a strategy of connecting distant regions with complementary production profiles, linking areas experiencing daytime with those in darkness, or summer with winter, effectively creating a planet-wide solar collection system. Ultimately, addressing intermittency requires a portfolio approach combining storage technologies across multiple timescales, enhanced transmission, demand management, and complementary generation sources. The technical pathways exist, but deploying them at the necessary scale represents an unprecedented engineering and economic challenge. The spatial requirements of a solar-powered civilization prompt important questions about land use and environmental impact. Unlike fossil fuels, which concentrate energy from ancient sunlight into dense hydrocarbon molecules, solar power harnesses diffuse energy in real time, requiring significant surface area for collection. Modern utility-scale solar farms require approximately 5 to 10 acres per megawatt of capacity, depending on the technology and geography. Extrapolating to global energy needs, powering the entire planet would require approximately 0.3% of Earth's total land area, roughly 1.6 million square kilometers. While this represents a substantial area, it equals about one-third the land currently dedicated to growing biofuels and less than half the footprint of global roadways. The geographical distribution of this solar infrastructure would likely concentrate in the world's Sun Belt regions, where solar irradiance exceeds 2,000 kilowatt-hours per square meter annually. The Sahara Desert alone receives enough sunlight to theoretically power global energy consumption many times over. Other prime locations include Australia's outback, the Arabian Peninsula, the southwestern United States, and Chile's Atacama Desert. Environments offer ideal conditions for solar generation: abundant sunshine, minimal competing land uses, and flat terrain. However, large-scale desert installations raise concerns about habitat disruption and microclimate changes. Research indicates that extensive solar arrays can increase local temperatures and alter precipitation patterns through changes in surface albedo and atmospheric circulation. Water use presents another environmental consideration. Photovoltaic systems require minimal water after installation, primarily for occasional cleaning. However, concentrated solar power systems traditionally use wet cooling, consuming approximately 800 gallons of water per megawatt-hour produced. Advanced dry cooling technologies can reduce this consumption by up to 90%, though with slight efficiency penalties. The materials required for massive solar deployment raise sustainability questions. Conventional silicon PV panels require high-purity silicon, silver, copper, aluminum, and glass, all energy-intensive to extract and process. Thin-film technologies like cadmium telluride use less common elements with potential supply constraints. Life cycle assessments indicate that solar panels typically repay their embodied energy within 1 to 4 years, depending on location and technology, yielding energy returns 20 to 30 times their initial investment over their 25 to 30-year lifespans. End-of-life considerations grow increasingly important as early solar installations reach retirement. The International Renewable Energy Agency projects that cumulative solar panel waste could reach 78 million metric tons by 2050. While silicon panels contain valuable materials like silver and high-purity silicon, recycling processes remain energy-intensive and economically challenging. The European Union has established regulations requiring panel manufacturers to finance collection and recycling, a model that may need global adoption. Rather than dedicating new land exclusively to solar, integrating solar collection into existing human-modified landscapes offers a promising approach. Rooftop solar can utilize already developed space, adding approximately 400,000 square kilometers of potential collection area globally. Floating solar installations on reservoirs and water treatment facilities reduce evaporation while generating electricity. Agrivoltaics, systems that combine agriculture with solar generation, can increase land productivity by up to 70% through complementary use, growing shade-tolerant crops beneath elevated panels. Transportation. Corridors represent another integration opportunity. Solar canopies over highways, parking lots, and railways provide dual benefits: electricity generation and reduced urban heat island effects. Some European bike paths now incorporate solar panels in their surfaces, though efficiency and durability challenges remain for such applications. The environmental calculus ultimately favors solar power, despite these considerations. The life cycle carbon emissions of solar electricity range from 15 to 40 grams of CO2 equivalent per kilowatt-hour, roughly 1/10 the emissions of natural gas and 1/30 those of coal. Solar power also eliminates the persistent pollution associated with fossil fuel extraction, processing, and combustion. The economics of solar power have undergone a transformation that few predicted. In 2010, utility-scale solar electricity cost approximately $378 per megawatt-hour. By 2024, that figure had plummeted to approximately $30 per megawatt-hour in optimal locations, a 92% reduction in just 14 years. This dramatic cost decline has fundamentally altered the global energy landscape, making solar the cheapest form of new electricity generation in many regions. This economic revolution stems from multiple factors. Manufacturing scale has increased by orders of magnitude, driving down production costs through automation and process refinements. Technological improvements have boosted efficiency and reduced material requirements. Financing costs have declined as investors gain confidence in solar's reliability and longevity. These reinforcing trends have created a virtuous cycle of expansion and cost reduction that continues today. The International Energy Agency now declares solar the cheapest electricity in history in many markets. However, these direct costs tell only part of the story. The true economic comparison must account for integration costs, expenses associated with managing solar's intermittency. These include storage systems, transmission upgrades, and grid balancing services. When these costs are included, solar's economic advantage narrows but remains compelling in many scenarios, particularly as storage technologies follow similar cost reduction trajectories. Capital requirements for a global solar transition would be enormous but not unprecedented. The International Renewable Energy Agency estimates that powering the world with renewables would require approximately $110 trillion in investments through 2050, averaging about $4 trillion annually. While this represents roughly 2% of global GDP, it compares favorably with current fossil fuel investments and would generate substantial economic returns through energy cost savings and avoided climate damages. Financing this transition presents both challenges and opportunities. The upfront capital-intensive nature of solar contrasts sharply with fossil fuels, where operating costs, primarily fuel, represent the major expense. This front-loading of costs requires innovative financing mechanisms, particularly in developing economies, where capital access remains constrained. Green bonds, sustainability-linked loans, and international climate finance commitments all play crucial roles in addressing this challenge. The economic transformation extends beyond electricity markets. Solar deployment creates jobs at approximately 3 times the rate of fossil fuel industries per unit of energy produced. In 2023, the solar industry employed over 4 million people globally, with projections suggesting this could reach 25 million by 2030. These jobs span manufacturing, installation, operations, maintenance, and associated services. The geographical distribution of economic benefits differs significantly from fossil fuel economies. While oil and gas production concentrates in geologically placid regions, solar resources are more evenly distributed globally. Nearly every nation receives sufficient sunlight to meet its energy needs, potentially democratizing energy production and reducing geopolitical tensions associated with resource competition. However, supply chain considerations complicate this picture. China currently dominates solar manufacturing, producing approximately 75% of the world's photovoltaic modules and controlling much of the upstream supply chain, including polysilicon production and wafer manufacturing. This concentration raises concerns about supply security and has prompted policies to diversify manufacturing across regions. Energy transition economics must also account for stranded assets, investments in fossil fuel infrastructure that may become unprofitable before their expected lifespans. The International Energy Agency estimates that a pathway to net zero emissions could strand approximately $900 billion in fossil fuel assets by 2030. Managing this financial disruption while ensuring energy security represents a significant economic and political challenge. The pace of transition varies dramatically by region. Developing economies face the dual challenge of expanding energy access while transitioning to cleaner sources. For the 2 billion people with inadequate electricity access, distributed solar often represents the most economical path forward, allowing these regions to potentially leapfrog centralized fossil fuel infrastructure. As solar penetration increases, electricity market structures must evolve. Traditional markets designed around dispatchable generation struggle to incorporate large shares of zero marginal cost solar electricity. Some markets have already experienced negative pricing during peak solar production hours, signaling the need for reformed market designs that value capacity, flexibility, and grid services. In addition to energy, the transition to a solar-powered world would fundamentally reshape global geopolitics, altering power dynamics that have persisted since the Industrial Revolution. For over a century, control over fossil fuel resources has defined international relations, sparked conflicts, and shaped alliances. A world powered primarily by sunlight would operate under substantially different rules. Unlike oil and gas concentrated in specific geological formations, solar energy is relatively ubiquitous, though not uniformly distributed. Nearly every nation receives sufficient sunlight to meet its domestic needs, potentially reducing energy dependencies that have long shaped international politics. Countries currently dependent on energy imports spend collectively over $2 trillion annually on fossil fuels, funds that could instead support domestic solar infrastructure. The Middle East, historically significant for its oil reserves, ironically possesses some of the world's best solar resources. Saudi Arabia receives approximately twice the solar irradiance of Central Europe. This geographical advantage could allow oil-producing nations to pivot from petroleum exporters to renewable energy powerhouses, though with substantially altered geopolitical leverage. Strategic competition has already shifted from controlling fossil fuel deposits to dominating clean energy supply chains. China's early and substantial investments in solar manufacturing have secured its position as the leading producer of photovoltaic modules, battery components, and critical minerals. In 2023, Chinese companies produced 85% of silicon wafers and 75% of solar cells globally. This manufacturing concentration presents national security concerns for many countries, spurring policies aimed at supply chain diversification. The United States Inflation Reduction Act allocates nearly $400 billion toward clean energy manufacturing and deployment, explicitly designed to reduce dependency on Chinese solar components. The European Union has similarly implemented a Green Deal industrial plan, offering subsidies to domestic manufacturers. Access to critical minerals represents another geopolitical consideration. While silicon, the primary material in conventional solar cells, is abundant, other elements like tellurium, indium, and silver face potential supply constraints. The geographical concentration of these resources, particularly rare earth elements essential for certain high-efficiency solar technologies, introduces new resource dependencies that could mirror traditional fossil fuel geopolitics. Control over intellectual property and advanced manufacturing techniques is emerging as a strategic advantage. Next-generation solar technologies like perovskites, organic photovoltaics, and advanced thin films could reshape manufacturing advantages, potentially allowing nations with strong research capabilities but limited manufacturing experience to establish leadership positions. Strategic choke points may shift from oil shipping lanes to electricity transmission corridors. Proposed continental-scale and intercontinental transmission networks would create new interdependencies and vulnerabilities. Projects like the proposed Australia-Singapore power link, which would export Australian solar electricity to Southeast Asia via undersea cables, demonstrate how energy geopolitics could evolve in a solar-dominated system. Energy water-food nexus considerations take on new dimensions in a solar-powered world. Water constraints in prime solar regions could limit deployment or increase conflicts over water resources. Conversely, solar-powered desalination could address water scarcity in coastline desert regions, potentially transforming habitability and agricultural potential in currently water-stressed areas. Climate refugees, people displaced by rising seas, extreme weather, and agricultural disruption, could number between 50 million and 1 billion by 2050, according to various projections. Nations achieving energy independence through distributed solar might better withstand these disruptions, potentially altering migration patterns and international stability. The governance of a solar-powered world would require new international frameworks. Today's energy governance institutions, like the Organization of Petroleum Exporting Countries, OPEC, and the International Energy Agency, IEA, evolved to manage fossil fuel markets. Solar dominance would necessitate institutions focused on technology transfer, grid interconnection standards, critical material supply chains, and international financing mechanisms. Military implications extend beyond resource competition. Armed forces historically dependent on petroleum supply lines could gain strategic advantages through solar-powered bases and equipment. The U.S. Department of Defense already recognizes energy security as a national security priority, investing heavily in renewable microgrids for both domestic installations and forward operating bases. The transition period itself presents perhaps the greatest geopolitical challenge, as declining fossil fuel demand threatens the stability of petroleum-dependent states. Before they can diversify their economies, regions like the Middle East, Russia, and parts of Africa face potential instability. Managing this transition while maintaining global security may require unprecedented international cooperation and support for economic diversification in vulnerable regions. As we peer into solar technology's future, several technological frontiers promise to transform our capacity to harness the sun's energy. Perovskite solar cells, crystalline materials with exceptional light absorption properties, have achieved the fastest efficiency improvement in photovoltaic history, rising from 3% to over 25% efficiency in just over a decade. Their ability to be manufactured using simple solution-based processes could dramatically reduce production costs and energy payback times. Tandem solar cells, which stack different semiconductor materials to capture complementary portions of the solar spectrum, have achieved efficiencies exceeding 47% in laboratory settings. Commercial versions combining silicon and perovskite layers are now entering production, with 30% efficiency targets within reach. These advancements could reduce land requirements by 1/3 compared to today's technologies. Beyond efficiency improvements, integration innovations are expanding solar's applications. Building integrated photovoltaics, BIPV, incorporates solar cells directly into construction materials, windows, facades, roofing materials, rather than mounting panels on completed structures. While currently more expensive than conventional, modules' declining costs and aesthetic advantages make BIPV increasingly attractive for zero-energy buildings. Solar fuels represent perhaps the most transformative frontier. These technologies directly convert sunlight and simple molecules like water and carbon dioxide into energy-dense fuels and chemicals. Artificial photosynthesis systems mimic plants' ability to split water using sunlight, producing hydrogen with theoretical efficiencies exceeding natural photosynthesis. Advanced photocatalysts and photoelectrochemical cells could eventually produce liquid fuels compatible with existing infrastructure, addressing transportation sectors difficult to electrify. Space-based solar power, though still speculative, could overcome terrestrial limitations entirely. Satellites equipped with kilometer-scale solar arrays would collect uninterrupted sunlight with intensity approximately 40% greater than peak terrestrial conditions. This energy would be transmitted to Earth via microwave beams to receiving stations. While prohibitively expensive today, declining launch costs and improved space manufacturing could eventually make this concept viable for specialized applications. The integration of artificial intelligence into solar energy systems promises to optimize everything from manufacturing processes to grid operation. Machine learning algorithms already help predict solar output, manage energy storage, and optimize maintenance schedules. As these technologies mature, they could enable fully autonomous energy systems that continuously adapt to changing conditions. Looking beyond technological development, societal adaptation represents an equally important frontier. Energy-efficient urban design could reduce demand while optimizing solar collection. Buildings oriented for passive solar heating and cooling, urban forms that minimize transportation needs, and conscious consumption patterns could substantially reduce energy requirements without sacrificing quality of life. The relationship between energy and economic development may evolve dramatically. Today's clean energy transitions typically follow the energy ladder model, where development proceeds from traditional biomass to fossil fuels to renewables. Emerging economies with abundant solar resources could potentially skip intermediate steps entirely, leapfrogging directly to distributed solar systems as their primary energy source. Broader technological convergence could accelerate solar adoption. The simultaneous advancement of artificial intelligence, robotics, advanced materials, and biotechnology creates synergistic opportunities. Self-replicating robotic systems could dramatically reduce solar installation costs. Biologically inspired materials could create self-healing solar components. Distributed ledger technologies could enable peer-to-peer electricity trading, making solar adoption financially accessible to more communities. Our solar-powered civilization would fundamentally differ from our fossil-based society in its relationship with entropy and time. Fossil fuels represent concentrated ancient sunlight, energy stored over millions of years that we've rapidly depleted in centuries. Solar power constrains us to current energy flows, requiring different patterns of production and consumption that align with natural rhythms. This constraint could ultimately prove liberating, fostering resilient systems that adapt to natural cycles rather than exhausting finite resources. The transition to solar energy represents not merely a technical substitution, but a profound reimagining of human civilization's relationship with energy. The ancient Greeks viewed the sun god Helios as all-seeing, driving his chariot across the sky daily, powerfully present yet ultimately distant. Our modern relationship with solar energy transforms this dynamic. We now actively harness Helios's power, no longer passive observers, but partners in the flow of energy that sustains all life on Earth. As we contemplate a solar-powered future, we confront fundamental questions about sustainability, equity, and purpose. Could we power the entire planet with solar energy? The technical analysis suggests yes, with the right investments, policies, and technological developments. But perhaps the more important question is not whether we could, but how we might use this abundant energy to create a more just, sustainable, and flourishing civilization. In the radiant light of the sun, we may find not just the power to maintain our current trajectory, but the wisdom to chart a new and better course, one that honors the delicate balance of our planetary home and the profound responsibility that comes with harnessing its fundamental energy source.